In our first seminar, we addressed issues through the lens of codes, EC7, EC8. In this seminar, we have tried to address issues of common interest through the lens of failures. And one of the most common among failures that we face in geotechnical engineering is landslides. So what is a landslide? I always like to begin with definitions, simple things, and then proceed to deeper meanings and things. A landslide in general is the movement of a mass, which may be rock, debris, or soil, down a slope, in the form of a solid block or a totally disaggregated mass or a combination of both, with a rate of movement that may range from something enormously slow to something enormously fast, because of a trigger that causes a disturbance to a previously established equilibrium. And it usually takes place along a specific sliding surface, whether it is an actual solid block or a disaggregated mass. It needs a specific surface that differentiates it from the stable mass below the landslide. What are the typical parts of landslides? The typical parts consist of the sliding surface itself, the toe, the scarp, cracks that appear usually in the scarp and may actually be full of water that is actually pressing the landslide block, and a water table, or more generally a pore pressure regime, that affects the equilibrium of forces or moments that we have in this landslide. They may be toe failure landslides, with the toe of the sliding surface coinciding practically with the toe of the slope, or they may be deep-seated landslides, where the toe of the sliding surface may be different from the toe of the slope, and they also have an inclined first part of the sliding face opposite to the inclination of the slope. And what do scarps look like? Scarps look like what I have here from some major landslides in mines. Landslides are not only relevant to civil infrastructure, but very relevant also to open pit mining. And I have some landslides from the Sesklo clay mine, one of the oldest clay mines in use in Greece, with very deep cracks at the scarp of the southwestern slide and also on the western landslide within this mine, plus a very impressive scarp in a landslide that took place in a monument, in the monument of St. Demetrius Bastion in Chania. And I have tried to make this visible and clearer on your pictures. Similarly, we can see some toes of actual landslides, the same before the toe of the western landslide in Sesklo clay mine in central Greece, a very impressive toe of the southwestern landslide in Sesklo clay mine, also a very impressive toe of the St. Demetrius Bastion, and to make a connection with what Professor Kyriazis Pitilakis was showing us before, an enormously impressive toe of a landslide in bentonitic clays in Paphos region near the village of Armou in western Cyprus. And to make this more visible to you, here we are talking about a bentonitic clay which on average has a liquid limit in the order of 130% and a plasticity index of 100%. And what do sliding surfaces look like? They can have the form that you see here in practically homogeneous materials, whether they may be of low plasticity or high plasticity. They can take the shape of interfaces between clay materials, as those you can see here and here, with the occasional finding of gravel that has been dragged along the sliding surface because of the very large movement that has taken place. And on occasion, they may also include specific organic layers that are found at the exact location of the sliding. Mind you, characteristics like these ones We can find them in many cores that we would like to split and have a look at them because of whatever has happened in the history of these materials. All the surfaces I'm showing here are actual sliding surfaces which have been verified by inclinometer measurements in these exact locations and depths that you see here in these boreholes. And how do we classify landslides? We can use the good old VARDS 1978 classification that basically uses lithology, geometry, and morphology. Lithology of whether we have a sliding mass of rock, debris, or soil, and the various types of geometries and morphologies that take place. Usually, we take much interest in the actual slides that may be rotational or translational. We can use velocity, which in my opinion plays perhaps the major role, and plays the major role because it dictates whether we can do something or not. We can have landslides which can be extremely or very rapid, with velocities that can have typical values like this. When we have velocities like this, there is practically no response possible there, that we can do something about it. The only thing we can do is either early identification and proactive stabilization. Similarly, in rapid to moderately fast landslides, again, practically we cannot do something technically when they take place, but at least we can evacuate. We can evacuate people in order to save lives. And in both of these cases, we can always add remediation measures post-mortem. The interesting part comes here. And it comes here because we have landslides that are either slow or very slow, and we can actually do something about them while they are happening. We can do maintenance, we can do stabilization, and so we actually do design for our stabilization measures. And even before design, we have to do what I consider the most important thing, and I will try to focus in the second part of the presentation, is to select the measures that we can use in order to stabilize them. And finally, we can have extremely slow landslides, which, yes, they are identified, but they practically have no measurable movements or movement rates, and there is no response necessary, except, of course, for keep monitoring them, in case there comes some sort of change. So some examples. A major rockfall, to my knowledge the largest rockfall that has taken place in historical times in Greece, 350,000 cubic meters, on the 10th of February of 2008, within a matter of seconds. On a slope, a gneiss slope, 280 meters high plus another 20-30 meters below the waterline, which was already standing there, totally stable, for something like 15 to 20 years after the construction of the Thessaloniki Dam. Similarly, again within a matter of seconds, and again on a February, by the end of this presentation, most probably will have a relation with the occurrence of landslides, where approximately we had a landslide of 20 to 25,000 cubic meters on the south slope of the Corinth Canal, which again took place within a matter of seconds, practically with nothing that can be done, and is associated with a soil behavior that in terms of strength and the evolution of strength with shear strain, it looks like this. Enormous peak strength, a peak strength that has a failure envelope that practically if we insert it in any kind of calculation, it's going to give us examples that are more than just acceptable, but with very little additional shear strain, it can have considerable loss of strength down to a post-rupture failure envelope corresponding to values that will practically make us believe why these slopes are actually standing. So yes, we can have these very rapid landslides associated with a soil behavior, soil strength behavior of this kind. And on the opposite, we can have enormously slow landslides with which you can live. And I have two examples, in fact, two examples that are very close to one another, along Egnatia Highway between the city of Veria and the city of Levkopetra, one of them being a landslide with a volume of approximately 5 million cubic meters moving at a rate of 1 to 2 centimeters per year, involving the highest unreinforced embankment in Greece, an embankment which is 55 meters high, and something like 250 meters away, another landslide in the order of 15 million cubic meters that is moving at a rate of 1 centimeter per year, and it takes with it the highway, the only alternative being the national road, 2 tunnels of the highway, and a fuel pipe, a military fuel pipe crossing between the two. But at these rates, with which we can live, and we have lived. We have lived already for decades, although design studies are already there for what we can do in order to improve the stability. This is the 5 million cubic meter one, the one here, and this is the 15 million cubic meter one with the tunnels that takes with it, the fuel pipe, and the alternative national road. So there is another classification that, in my opinion, plays a major role, which is according to size, and I have here a reference for a recent work by McCall and Cook, who have tried to produce this table and also a diagram relating the volumes with the area, the associated area, and carry out a classification which they used in their work in order to assess how one does something with these landslides. And I want to continue with some examples to make my case for some things that must be said about landslides. So far, I think that we have all understood that they are relevant to civil infrastructure and mining, and of course they are relevant to the countryside, and they can be very small. A typical, one could say, John Doe landslide anywhere in some project I have for comparison the size of a machine here to understand what we're talking about, and large landslides like the ones I was showing before. But they are also relevant to private property. And here I have an example from a landslide at a location called Basale on the island of Skiros in central Aegean Sea, where you can see a private property with a huge scarp behind it, and all this took place within a matter of a few hours. The yellow line shows the original position of the local road, and the dust red line showed where this road went within a matter of hours, with the upper property moving tens of meters, and another property that used to be here moving and rotating several meters and several tens of degrees. And here we have an even more dramatic photograph of where this private property used to be before the landslide. Plus, the landslide in the Bentonitic clay in Paphos I was showing before, which here I have an impressive view of the toe, but at its scarp, it has a number of villas, which you can see here, with a yellow arrow indicating the actual scarp and the associated depression between two series of villas, which is in the order of 5 meters. And this is from a review under work by Coulermo et al. In 2025, where we can see the map of this landslide in previous aerial photographs, how these villas were built in the early 2010s, and how these have been seriously affected, and how many of them are actually moving, and they are moving seriously along these landslides with irreparable damages. Okay, so you made your point. Landslides can be relevant to civil infrastructure, to open pit mining, and private property. But come on, only in the countryside. Okay. I will keep traveling you in Greece and Cyprus, and I will now take you to the beautiful city of Chania. Beautiful city in western Crete, which has an old part at its center, the Venetian city of Chania with its fortifications, the major western moat on the west side, and some of the inventions of Michalis Bardanis, the Genovese engineer who was involved in the design and construction of these fortifications, which were the heart-shaped bastions that could help the Venetians defend better their fortifications against their enemies, plus the existence of an elevated structure behind uphill of the heart-shaped bastions, which was known as a cavaliere, which could help elevate the cannons of the time at a much higher altitude so that it could have a larger range. I think I pressed it too much. They could fire at a higher range to the enemies that were attacking the city. And these are actually some very impressive structures. A heart-shaped bastion can stand something like 21, 22 meters above the dry moat, and the cavaliere, the elevated bastion uphill of the main heart-shaped bastion, can stand to another 16 to 17 meters above the plateau at the top of the heart-shaped bastion, with this area here, the crest, used at the time in order to place the cannons to fire against the attacking enemies. And so, okay, again on February, we have the first eastern failure that took place on the 11th of February 2017 in a main street in the old city. Here the victim was a parked car right there. 3 days later, again in February of 2017, on St. Valentine's Day, another western failure shown here that takes all the pavements and sidewalks that were used by people to go to the elementary school just across the street where I'm standing here in order to take the photograph. And some 2 years later, 28th of February of 2019, okay, there is obviously a relation with February. We now have to find causation here, but okay. Which again hits the northern part of the Cavaliere, destroying all the pavement where tourists and visitors in the city pass in order to go from the western side to the center of the city. And if this doesn't look very, sort of, say, urban, 33 years ago, in Thessaloniki, during the second National Conference on Geotechnical Engineering, Kavounidis et al. Presented the case of an actual landslide in Kypseli. For those knowing Athens, Kypseli is the most densely populated area of Athens. And there was this plot where an excavation had been made in order to construct a new block of flats adjacent to an existing block of flats. And when the final part of the excavation, just another 1.5 meters, took place, a landslide occurred, a typical landslide with a scarp, with a toe, with a sliding surface, leaving a footing of the adjacent block of flats with an estimated, here is the actual adjacent block of flats with the landslide that took place right below it, with only a factor of safety of 1.24 for the footing. A berm was placed immediately in order to stabilize this, and eventually a concrete pile wall was constructed with a very stiff pile cap at the top in order to stabilize the area here, make sure that nothing happens to the adjacent block of flats, and eventually build the new block of flats right next to it. So, to put things right, landslides are relevant to civil infrastructure, open pit mining, monuments, and private property, both in the countryside and in urban environments if we are not careful enough, period. And what I'm about to present in the rest of my presentation is a few basic things about the identification and investigation, not much on that, but I will focus more on the selection and a possible use of some logical diagrams for the selection of stabilization measures. So for identification and investigation, we are going to rely heavily on engineering geology and our engineering geologist colleagues with their reports and mapping about what is happening and where, the identification of mechanisms and triggers, use instrumentation, a lot of instrumentation, inclinometers and instrumentation to measure pore pressures. What do these lovely things look like? Our inclinometer pipes where we will send our inclinometer probes through in order to measure the type of movement that we get at certain depths, which may be something clear, like what you see here on the two axes, or we may have something developing in two different depths, and we must be prudent enough in order to recognize what is noise and only actual depths of movement that are taking place. Use lots of instrumentation for pore water pressure that may be simple well piezometers or more complicated piezometers with Casagrande type tips to measure pressures at specific locations, which, if we are interested in continuous logging and also very fast response, we can also substitute them for vibrating wire piezometers that we would locate at specific depths. And then, how do we make our analysis? Usually, even until today, we will use limit equilibrium and various geometries in order to make assumptions, essentially, of how our sliding blocks are moving. We may have the infinite slope, we may have certain triangular or trapezoidal sliding blocks that we are considering, and we are trying to find the equilibrium, or even parts of circles where we could use simpler methods in order to analyze them with undrained shear strength and everything, or eventually use the slices method of limit equilibrium analysis, where we essentially cut in slices our sliding blocks and we formulate our equilibrium equations that eventually lead, as George Gazzetta said before and we like to use, to a total factor of safety that is practically the ratio between the sum of resisting forces of moments over the sum of driving forces of moments. And just a comment on the partial factors, too many times, if we use the partial factors, we will eventually get something wrong with the position of the estimated critical surface. Because it is not just a matter of finding a number and we are comparing just the total factor of safety with the same result that we would be obtaining from partial factors, but when we are carrying out an analysis like this, the actual values that we are using in our calculations are going to affect the position of the critical sliding surface that we are considering. So this discussion about partial factors and total factors when it comes to landslide analysis and slope stability is not just a matter of comparing numbers. It's a matter of comparing estimated sliding blocks, and the partial factor method can very easily lead us to a very misleading location of a sliding surface, which itself will then lead us to a misleading selection of stabilization measures. And what happens in our landslides is that we begin with a failure envelope corresponding to some peak strength, and as our shear strength increases, this peak strength drops on occasion, as I showed you with the Corinth Canal marls, very rapidly to a failure envelope corresponding to the post-rupture strength. And if we keep increasing our shear strength along our sliding surfaces, we will eventually totally orientate our clay platelets and get down to a strength corresponding to the residual shear strength of our clays, which is the minimum shear strength failure envelope that we can have for our soils. And how would we measure this in the laboratory? We would measure it using the ring shear, either in the good old form of the Bishop ring shear apparatus or the modified Bromhead ring shear apparatus, which is smaller and uses reconstituted soil, that practically allows us to apply infinitely high shear strain. Come on, why do we need it? Because of this we need it. And when I'm showing ring shear apparatuses, I always like to have this picture right next to them to remind people of the kind of shear strain that we must remember that can be applied in our soils and be there. Of course, any presentation on landslides does not expect itself unless it talks about the back analysis. The back analysis is the analysis where we have managed somehow to locate with our inclinometers, with our mapping, a good estimate of our sliding surface, and provided that our landslide has moved enough, we can reasonably assume that it has a zero cohesion intercept and only a single value of a residual angle of shearing resistance that we can find by trying to calculate a factor of safety equal to 1. This doesn't necessarily compare with the laboratory test results. The usual rule of thumb is that we may expect a difference in the order of 2 to 4 degrees. And then what do we do with all of these? We must understand the effect of external forces. Any force applied downwards close to the scarp is destabilizing. Any force downwards applied at the toe is stabilizing. And we may have forces due to seismic loading. Okay, for my next presentation, I'm going to erase the vertical component. Okay. But these are things that we have to consider and we have occasionally done. And when it comes to our remediation measures, our factor of safety increases. By any way we can decrease our driving forces, any way we can increase our resisting forces, and if we can, by both decreasing driving forces and increasing resisting forces. And how will we do this? We can do it by structural elements being piles that we will place in our sliding blocks in order to contribute resistance. They can be barrettes, stiffer structural elements. They can be shear keys being structural elements that we apply only in the vicinity of our sliding surface. An obvious question, what happens if something else is mobilized above those shear keys? There can be several types of bolts, soil nailing, and pre-stressed anchors that we are applying in our sliding blocks in order to either activate a new force that we are applying or wait for the sliding block to move until some resistance develops. And there we have some considerations that we must take into account that limit equilibrium cannot really take into account. And this is where finite element method, and even more importantly, the material point method can become more useful. Okay, if we have a large difference between the modulus of elasticity of the sliding mass and the stable mass below it, we place our pile, the pile is fixed, and so by bending, it is going to provide some additional resisting force to our sliding block. Fine. And here I have an example of an actual inclinometer placed inside a stabilizing pile of a landslide, which was fixed. We can see here a total fix of this pile with no movement at all, bending, and this pile contributed to the stability of this landslide. A fair question is always, what is going to happen to the part of the landslide below, downhill of my pile wall? Plus, what happens if the modulus of elasticity of my sliding mass is very, very small? And it's that usual question, okay, I have placed my piles. Why is my structure up here in the scarp still moving? Which actually makes sense, because if something is very soft and we placed some stiff structural elements some 200 meters away, by what time, if ever, is actual movement going to stop in a structure very high, very far away from that structural element? And in a similar manner, if we have a very small difference in the value of the modulus of elasticity and both values are small, then the pile cannot even bend, it will actually start turning. And again, we have a similar fair question like that. When is eventually going this structural element going to have any effect at all on my structures up here? And if not structural elements, then what? Excavations at the scarp, berms, stabilizing berms at the top, lowering of the water table, or even trying to improve the properties of the soil along the sliding surface. Here I have some types of drainage measures, some horizontal drainage boreholes, which need a considerable slope here so that they can take an effect. If this slope is very mild, then we need something enormously long to have an effect. And if it is enormously long, who knows if it's going to actually have an effect on the water table. We can have stronger solutions like drainage tunnels with all the fans of boreholes above it in order to lower the water table below our sliding surface. We can have various types of wells that may be pumped, something that is very tricky when it comes to the actual electrical design of the pumps. We can have connected vertical wells, then we only have to pump the vertical well that is at the toe of the landslide. And on occasion, especially for slow-moving landslides that have been affected by the erosion of their toe, we may have the opportunity to actually drain them by gravity because there is a permeable underlying layer below the landslide that the landslide during its movement, it has actually covered it in its geological history. And here I have an actual photograph of a type of a well. Again, watch out for the deformation of buildings and structures. Whenever we resort to decreasing water tables, to lowering water tables, the answer that we have, the question we have first to answer is, can the buildings or structures that we may have there sustain the deformations that will be induced by the decrease of the water table? And I use this example. If we were discussing stress-strain only, and we showed a kind of load distribution like this, everybody would say, oh wow, what sort of stress distribution is this? It's going to have some serious and very strange deformation patterns in our soil. And then people will tell me, come on, how is this going to happen? Well, this is going to happen if we are pumping. Because pumping and lowering the water table like this actually creates a distribution of increased effective vertical stress like this. And we have to take into account what is going to happen due to differential settlement to any structures that are within the effective radius of these drainage wells. And now we're starting the important part of the presentation. Up till now, it was just introduction. Many times, we focus on the identification, the investigation, the analysis, the calculations. Beautiful, beautiful things, all of them. Fine. But how do we select the measures that we are going to use in order to stabilize? If somebody comes over and tells us, oh, you know, this landslide, piles. Okay, fine. I will open the books, I will open the papers, and I will start doing calculations. Okay, drainage. I will do my calculation period. How do I end up with the actual measures I'm supposed to use? And I have made this effort to try and put this on a logical diagram. I know it's late, but I will kindly ask you to try and follow me because I have some nice examples. Question number one. But when we do not have structures that are seriously affected, if we have structures affected, there is a different logical diagram. What is its size? Is it small, medium, large? Let's do the simple thing. If it's small, and if totally removed, it will not create a larger phenomenon or affect any buildings, then remove the whole thing. Don't think for a second about it. Just remove it, excavate, and take it away. If it's going to affect something larger or your buildings, then no. You have to go to the next logical diagram, which introduces what happens to landslides that are affecting structures. And if it is medium or large, introduce the role of the pore pressure regime. Does it play a role? Yes. Will the pore pressure decrease affect building structures? Yes. Go to the next figure. No. Consider the constructability of drainage. It doesn't play a role. No. Okay. Can excavations or a toe berm trigger something larger? No. Fine. Consider the constructability of scarp excavations and toe berms. Yes. Fine. Is there considerable difference between the modulus of elasticity below and above? If yes, consider the constructability of structural elements. If no, introduce the value of the modulus of elasticity and again go to structural elements, but at the same time considering what happens to deformation. Examples. Here we are. Small, if removed, no consequence, go ahead, remove it. Here it is, D1 landslide in Metsovitikos Valley, the one that Loretta loves, 60 meters wide, 6 meters deep, 18 meters high slope. Remove the whole thing. Here it is immediately after the construction, and here it is 25 years later. A design performed by none other than Georgos Belokas, who is standing here before us 25 years ago. Could we do this here? No. Could we do this here? No. But for all of this, you would have been led along other paths on the logical diagram. An example. What is the size of the landslide? Medium. Does the pore pressure regime play a role? No. Can excavations or a top berm trigger something larger? No. Fine. Consider the constructability of a scarp excavation and top berms. Here it is. A landslide, 200 meters long, 100 meters wide, 70 meters deep. An excavation and a scarp. We practically use the same material to construct the berm. Here it is. Stable even after 25 years of its construction. Now let's say that we somehow activate the effect on structures. Then we have created a different logical diagram which first starts with a pore pressure regime. Will the pore pressure decrease cause unacceptable deformations? If the answer is no, go ahead and consider the constructability and time to have an effect of drainage. If yes, and also if the answer here is no, consider excavations or top berm. If the answer is no, then go ahead with designing excavations and top berms. If yes, then consider the size. If it is small, you can eventually think about structural elements. If it is large, you may have to consider seriously to abandon this area. And here I have again only two examples. Does the pore pressure regime play a role? No. Can excavations trigger something larger? Yes. What is the size? Small. Is the modulus of elasticity large? Yes. Use structural element. Here it is. A structural pile wall that was used there in order to stabilize this and the adjacent block of flats. Does it play a role, the pore pressure regime? Yes, it does. Fine. Will the pore pressure decrease cause unacceptable deformations? Yes. Can excavations or top berms trigger a larger phenomenon? Yes. What is the size? Large. Abandon. Here it is. 300 meters, 100 meters wide, 25 meters deep, in a material which has 130% liquid limit and a modulus of elasticity which is measured in the order of 2 to 3 megapascals. What exactly are we going to try here in order to stabilize this? No other option. Abandon it. I will stop here. I would like you, when this becomes available, both the PDF and the recording, to come back with some feedback, because this is something that I am trying to introduce, especially to younger engineers that come to work and deal with landslide phenomena. And instead of conclusions, I will just try to put some of the Michalis rules that I have been using all these past years. Trust your geological mapping. Trust your geotechnical investigation, your monitoring data. Believe big. If I had €1 for every time I have heard, oh, come on, it cannot be up to there. It cannot be this deep. It cannot be this wide. Why do you ask us for an inclinometer up there? It's rock. Just €1. Just €1 for every time I have heard this comment. I would be a rich man. So believe big from the beginning. If it ends up smaller, fine. It ended up smaller, but believe big from the beginning. Find the bloody clay. Period. find the clay. And if you didn't find your clay, go back and look for it again. No landslide that respects itself has nothing to do with clays. All landslides that respect themselves are seriously affected by clays. And once we do this, try by using something like the logical diagrams I showed you before. Consider the rate of movements, the effect of movements on structures, the size, the effect of pore pressures and their decrease, and finally, anything that you can do with structural elements. Thank you all. A big thank you to this superb team of colleagues that I've had throughout the years in Edafos Engineering Consultants. And for those of you who would be interested, some references that you may find in the PDF and in the recording later on. Thank you very much.